I should mention that I don't work alone, though. I work with a very talented group of people, some of whom are listed here. And so some of the things that I'm going to tell you about today are actually the work that our entire group has been working on for the last year since we first got involved with CUDA. So I'm going to tell you a little bit about several different algorithms that are related for calculating electrostatic fields around molecules. And then after I get done with those, I will switch gears and talk a little bit about NAMD, which is a parallel molecular dynamics code. So one of the things that's very important in studying how biological molecules work is understanding the electrostatic fields that surround these molecules, because the electrostatics actually controls how the atoms in these molecules interact. So these are used in constructing the models that we actually run simulations of on the big supercomputers. To build these models, we have to place ions in this electrostatic field and to set up the experimental conditions in exactly the same way they really are in the natural biological system. So for this particular calculation, we are going to sum potentials for all of the atoms in the entire space into each of many little grid cells on a lattice that surround the molecule in this entire cube. So I'll show you how that's done. So it's actually a very simple calculation in its root. So for each lattice point where we want to compute an electrostatic potential, we take the we calculate the potential contribution from each atom in the entire molecule, and we take its charge divided by the distance from that atom to the point being considered, and then we sum that into the lattice point that we're calculating. So you can see it's very easy, but we actually have to do this for all of the atoms and all of the grid points. So it's sort of an order n times m operation to do this for this whole grid. So it's very computationally demanding. So on a CPU, you have to decide how you're going to structure your code to use the cache efficiently, because on a CPU, that's the thing that gives you the higher performance. So you have to choose which of the loops are going to be on the inside and which of the loops are going to be on the outside. And this has an effect on the GPU as well, because the GPU has special features like the constant memory that Wen Mei just mentioned. It has a small shared memory that you can use within a thread block. And so if we want to use those features of the hardware, we have to make various decisions about whether we're going to process grid points in the inner loop or whether we're going to process atoms in the inner loop. So we have that choice. Well, since the atom list is much smaller than the number of lattice points in the typical problem that we're solving, the atoms are easier to cache. And because they're read-only, they don't change, they are easier data to put into one of these special memory systems. So the lattice point coordinates are implicit, so we don't have to store them. We can actually calculate them on the fly as the algorithm runs. And by, Wen Mei mentioned pre-calculating various things that are invariant from one iteration of a calculation to the next. If we pull all of those things completely out of the calculation, that can make the whole thing run that much faster. So in this case, we pre-bake the coordinates of the atoms and the grid points so that they're in the same coordinate system, and it makes the math that we do in each iteration that much simpler. And then another trick that we can use is to pre-calculate portions of the distance vectors for each of these atoms versus particular rows, columns, and planes of the 3D map. So on the CPU, another strategy for getting performance is to use SSE instructions, which are basically like a tiny little 4-element vector. And so getting those things oriented right is important for the CPU as well. So here's a very simple piece of C code that calculates one slice of one potential map. And basically, you see as input, we get a big array, which is where the results are going to go. We have the dimensions of the grid, so the coordinate system that we're using, the grid spacing, what plane of the 3D cube we're processing, a pointer to the atoms, and the number of atoms. And so we're basically looping over these grid points in the 2D slice of this 3D grid. And then within the innermost loop, we're looping over all the atoms, computing the distance from the current grid point to the coordinate of that atom, computing the distance from that atom, and then scaling the charge, adding it to the total potential energy, and then we proceed doing that until we're done. So you can see it's actually a pretty simple piece of code. Now this is the slowest imaginable implementation, but it's easy to read, so that's why I've shown it to you. So if we want to run this on the GPU, we have to change things around a fair amount. So just to tell you what we're going to get at the end of this, by making some of these transformations, we will basically adapt the simple CPU kernel that I just showed you to running on the GPU, and we'll decompose it into tens of thousands of independent threads, and those will then be multiplexed across the hundreds of processing units on the GPU. And we'll ultimately get a speed up of about 44x, which is very good. You saw how simple a piece of code that was. That is actually, it's difficult to get something that small to run at that high rate of speed with no bottlenecks and no hiccups. So I'll show you all the tricks that we use. So for our purpose, single precision floating point is adequate. If we want better precision, we can use things like compensated summation, ordering the summation so that small items are added to small items, large items are added to large items. Doing that summation in a better order can give us better precision. So we don't necessarily need double precision to do this kind of calculation. And this algorithm is sort of the starting point for many similar grid-based algorithms, other electrostatic field calculations. So that's another reason why it's an interesting problem. So if we look at that original code I showed you, one of the first things we notice is that there's a low ratio of floating point operations compared to the number of memory loads and stores that need to be done to do the calculation, at least for a GPU. For a CPU, it's okay, but even then, it could be better. So we will, in a few slides, I will show you ways that we can increase this ratio tremendously and take advantage of all the ALUs around the GPU. So the innermost loop that processes those atoms is going to consume operands very quickly. So we'll be very concerned about finding ways to reuse those instead of reloading them from the global memory system or from other means. So for the GPU, the things that we're going to try to utilize are the constant memory. We want to avoid shared memory bin conflicts and try to overlap global memory reads with computation so that we hide that latency. So one of the other tricks that we will use is we will, instead of calculating a potential field that's the exact size that the user requests, we will actually pad it out so it's an even multiple of the number of threads in each thread block. And that way we eliminate having to have special arithmetic to deal with the edge conditions. It's better in a way to waste a few threads on the edge than it is to slow down the entire calculation for thousands of threads. So that's a little trick we can use. It has an added bonus of assisting with memory coalescing because now we have an evenly sized tiling and there's no special case to handle, and the way the potential map is written to memory works out perfectly for the GPU's coalescing. So sort of a pictorial representation of this is we start with an empty potential grid that has no data yet, and I've shaded the blue region is the area that we will eventually fill with results. The red region are the padding area where we'll have threads that are doing calculations, but they're going to produce results that we won't end up sending to the user, so that stuff will be thrown away. And then we begin with the atom coordinates and charges on the CPU, and what we will do is we will send those to the constant memory in about 4,000 atoms at a time. As Wen Mei said, you can only store about 64K of data in that constant memory, so in order to process the entire molecular structure, we go through in batches of 4,000 atoms at a time, running that loop, calculating their contributions to the grid, writing that out to global memory, and then repeating the process over and over and over as many iterations as are required. And then when the computation is complete, we read this back onto the host memory, we pull out the portion of the calculation we were interested in, minus the padding, and then we have the final result. Any questions so far? Okay. Yes, sorry. So in this particular case, you could have, this is a simple example because actually you can see the potential field that we're calculating completely surrounds the molecule. But there are definitely cases where you can have, you're interested in calculating a potential field in a subregion of space, but you might be collecting the contributions from a molecule that's much larger than the region you're computing, and vice versa. So you could do both of those. But they don't really have an effect on the way the computation is structured. So actually, it doesn't have any attendant problems associated with it. So for the first implementation, well, I didn't get into any of the biological details, but the catch is many of the approximation methods do not give us an accurate enough solution to place ions in structures like viruses or RNA. The positions of those ions are very critical, and if they're computed incorrectly, they will bind themselves to part of the structure where they should not be. And when you start running a simulation of them, they will get stuck, and it will be an unrecoverable situation because then the field is so strong they're stuck there. And we did a lot of experiments with this, and and I will show you in a minute, we have another method that has better time complexity that has a sort of a trade-off in the accuracy of the summation. But this one, we knew we could get the exact answer modulo the precision of the floating point that we were working at and the summation ordering. So, well, for the systems we were simulating, there were millions. So, this is getting too technical for the rest of the group, but I'll tell you afterwards. There are good reasons. So, the way that this calculation is decomposed onto the GPU, we have basically in the simplest code that I'll show you first, we have one thread for each electrostatic potential lattice point, and it basically does the summation for all the atoms that are in the constant cache for each pass of the multipass algorithm. And you can see how each of the thread blocks is tiled into a grid, and once again, you can see the border padding at the edges. So that's pretty straightforward. So there's a one-to-one mapping of threads to lattice points. So the simple implementation actually performs amazingly well. This was one of my first versions of this code, and I believe it only performs about 30% of what I will show you in a minute. But that's 187 gigaflops, and that's about 19 times faster than the best CPU version we could write, which used SSE and every trick in the book. So that's not bad. So this is taking advantage of the tremendous memory bandwidth of the GPU. We're using the constant memory to broadcast the atom coordinate data and the charges to all of the threads in the thread block, which basically amplifies the bandwidth that the GPU has even further. And then we have to do this multipass algorithm, which is unfortunate, but it actually doesn't present a performance bottleneck. And then each time we get done with one of these slices, we have to copy it back to the CPU. So there's a little bus transfer going on, but nothing to worry about. So this is what the GPU version of the kernel looks like. You'll see that it's actually very similar in the innermost loop to the way the CPU kernel looked. In this case, we have a nice little reciprocal square root function, which is a feature that the GPU has that, as somebody was saying, is an unfair advantage, but obviously very beneficial. Because this kind of calculation, reciprocal square roots, this happens everywhere in molecular dynamics and particle simulations of this sort. So this becomes sort of the time-limiting loop right here. And so you can see we're still loading the atom coordinates multiple times. Since we're calculating it for a plane, we can store just the z-plane coordinate and we save that calculation. But this is basically where we're at. So how do we make it run even faster? So one of the things that Wenmei mentioned earlier was loop unrolling. I'm going to show you a different kind of loop unrolling. So they call this loop unroll and jam. And the idea here is rather than unrolling the inner loop, we're sort of going to unroll the outer loop into the inner loop. Yes, you had a question? Well, you can do something similar in SSE, but it's a two instruction stages. But we were using SSE very efficiently. In fact, I worked very hard. Yeah, and the other thing I should mention is the CPU was disadvantaged because it has nowhere near the memory bandwidth that the GPU has. And with one core is easily able to saturate the memory system on the CPU. So anytime the other cores go out of cache, it's sort of game over. So this was another reason why this code runs very well on the GPU. So anyway, we unroll the outer loop into the inner loop, and so instead of processing one grid point with each of those pieces of atom data, we're now going to contribute that potential to several grid points at a time. And so the way we're doing this is we're retaining the components of the calculation that are the same from one grid point or one lattice point to another. So that would be the atom charge and, say, the y distance component and the z distance component. We can already add those up. And so the only thing that's changing from one lattice point to the other is the x coordinate or the x partial distance vector. And so that's the only thing that's changing. So we can basically unroll that. And then you'll see what we get is something that looks like this. So we have to do we pre-calculate the part that is the same for everybody, and then we make the 4 different x distance vector components, and then we just have the reciprocal square roots and so on. And now you can see the loop is much bigger, and there's a trade-off involved here because we're consuming a lot more registers. But the benefit is we have reduced the amount of redundant loads of this atom data. Even though it's coming out of constant memory, which is very fast, and it's being broadcast to all the threads, it's still not free. So if we can reduce the number of times we're redundantly loading things, even if it's almost the same speed as a register, it's still not free. So this is a tremendous performance benefit.
Yeah, so John, we talked about a similar technique for matrix multiplication. This was the relative of that calculation where you have each thread to calculate multiple data points in the matrix multiplication case yesterday. Okay, so these are similar techniques.
And so that's called unroll and jam, that idea of pulling the outer loop into the inner loop, spending more of our registers to reduce the number of redundant loads and stores. And so that's the trade we're making here. So another observation is that as we compute more than one lattice point per thread, we are reducing the amount of concurrency that's available to us in trade for better single thread performance. So that's not free. If we go too far with this, we could consume all the available concurrency and we might end up with GPU SMs that had nothing to do. So there's a limit to how far you would want to go with this, even if you had an infinite number of registers. So that's one thing to be aware of. And the other reason is because as that tile, the computational tile gets larger, that has the deleterious effect once we get to the edge where we have that border padding. If our tile is twice as wide as it was before, the penalty for having a map that doesn't evenly divide into the number of thread blocks is greater because you have a larger statistical likelihood of having a very large padding area. So that's another reason why you want your thread blocks and their resulting computational tiles to be smaller. So you can see now instead of a square-sized thread block or square-shaped computational tile that had a one-to-one relationship with the thread block, now we have a more rectangular-shaped tile, and the size of the padding area is going to be wider than it was before. Another thing that I should mention is we don't just unroll that x direction in immediate neighboring x coordinates. We do one special thing, which is rather than computing the next one over, we compute one an entire half warp over, and the reason for that is it gives us a coalesced memory pattern. So instead of doing these 2, 3, 4 in a row, we skip by that entire half warp, and then we retain coalesced memory, and so that gives us much better performance. So after having done that, the G80 GPU, which has a theoretical peak hardware performance of around 340 gigaflops, we're getting 291 gigaflops just in that inner loop. So not counting the other instructions like the loop instructions and so on. That's actually quite good. So this is doing 8 lattice points at a time, guaranteeing coalesced memory access, and basically we're loading and storing those 8 points at a time at the end of each of those loops. It's a much longer piece of code and it consumes a lot more registers, but it's at the balance point for where that algorithm gives excellent performance. So I was going back to what I said before. You remember we were making a trade-off between the available concurrency and the performance of one single thread. This is an important thing to observe because when you develop a kernel for a particular problem, you have to consider the range of problem sizes that you think are important, and you might be able to parameterize the same kernel several different ways so that it performs well for a small problem, a medium problem, or a big problem. And this is a concern because with the GPU, we need to have enough concurrency in the formulation of our kernel that we can fully occupy all the functional units on the device. So we want to have enough thread blocks, large enough thread blocks, and a big enough grid that we saturate the device with work. Until we saturate it with work, you will get a runtime curve like this one that's relatively flat. Once we have enough work to keep the GPU busy, you'll see the runtime increase along a linear slope, and then you'll be fully utilizing the device. So you can see here there's a region where the problem size is so tiny that it's actually faster to run it on the CPU because there's so little work. It actually takes more time to set things up on the GPU than it would to compute it on the CPU and return a result. So until we get to that crossover point, we would want to use a different strategy. And in the next slide, so in this region, you can see the GPU is doing 40 times the performance of the CPU, and that's because we've given it enough work to be effective. For our problem of interest, the range we were interested was 10,000 to millions of atoms. So this kernel was fully parameterized for the size we cared about. So here's another graphic that sort of shows the same concept with a variety of different CUDA kernels parameterized in different ways, and you'll see that they have this spiky-looking graph. The spikiness is due to the number of thread blocks in the grid, not evenly dividing out into the map that we're computing. So when you have, let's say, 127 thread blocks of work, but you have a 16-wide GPU, the last time through, some of those will be idle and they won't have anything to do. Or if you had 121, let's say, would be a good example. So the last time through, about half of the units on the GPU are idle. When that happens, you get a lower performance than when you happen to hit one that divides in evenly. So you can tweak your kernel to improve this. So in our case, we had different kernels, one for smaller sized potential maps, and you can see this one outperforms all the others in this range. And then another kernel that was tuned for the larger size maps. And so that's another strategy you can take. As far as the time involved, this was the first kernel I wrote, actually. Like I said, it was about 15 times faster, about 33% of what was possible. But that's not bad. It only took me a few hours of work, and you can see the CPU kernel was down here. So there's a huge difference in the performance. So the next thing that we want to do is be able to decompose this problem across multiple GPUs. So this is a much coarser level of parallelism, and the way we'll do that for this problem is by taking that 3D potential map and taking individual slices and cyclically assigning those to different GPUs. The map slices are fairly large, and so one nice attribute of them is we can compute multiple of these slices at once, and the shared memory communication that has to happen together, gather them all together, doesn't present a problem with false sharing in shared memory. So the test machine I used for the first multi-GPU calculation is shown here was just a little typical PC, but with 3 GPU cards in it. And since the amount of computation that we're doing is relatively large compared to the amount of memory copies back and forth between the host and the GPU, even though we have on this particular machine a PCI Express version 1 bus and slots that aren't even 16x on all 3 of them, the bus wasn't a bottleneck at all because we had a quadratic time algorithm and a linear amount of input data. So that's not an issue for this kind of code. For some codes, you have to think about how much I/O you're doing to the host because that could be a bottleneck, particularly if you have 3 or 4 GPUs. So with 3 GPUs, we were getting about 117 billion atom evaluations per second, and that's about 131 times faster than a CPU core. And this machine only drew about 700 watts. So this, to tell you a story, this allowed us to do calculations for these virus structures that would have taken a week on something around, I think, 110 processors on an SGI Altix. So by doing, and we could then do them in 27 minutes with 3 GPUs, doing it the hard way with this quadratic time algorithm. Doing the same thing on newer GPUs. This is the NCSA GPU cluster. We get over a teraflop with 4 GPUs there and a larger speed up. And with the latest generation of GPUs from NVIDIA, we're approaching almost 2 teraflops with 4 GPUs and a speed up of 271. So you can see that basically once you've got a highly tuned CUDA kernel, if you can then peel off large chunks of coarse grain parallelism, you can then use multiple GPUs and you can get unbelievable speed up. So we can do things now that, one of my colleagues, when I talked to him about how far these things had progressed since he first came to my office and asked for my help, he said, if you came to my office and told me that you would be able to do this in 27 minutes on 3 GPUs, I would have told you that you were insane. And then I told that story to David, and he said, well, that's what I'm here for, to bring insanity to science. So to improve things further, that was an excellent algorithm to get us started. We knew that the floating point behavior of that algorithm would give us predictable results. We didn't have to worry about the approximations giving us bad ion placements that would be unrecoverable later in simulation. But the next thing we wanted to do was replace that code with something that had linear time performance that was, so the runtime of this calculation, rather than being quadratic with the number of atoms, is just linear. And so the change we're going to make is instead of summing all of the atoms to each lattice point, we're only going to sum the atoms within a particular distance. And that's because the potential that's contributed by each of these atoms, of course, is decreasing markedly with distance. And so it's only the ones in the near vicinity of this lattice point that contribute large magnitude potentials. As they get farther and farther away, their effects are sort of blurred, and we can safely ignore them beyond a certain point. Or we can use a different two-stage technique. So in this code, instead of using the original formulation, we now have the similar thing, but we have what's called a smoothing function that helps us switch between this cutoff short range part and a separate piece of the algorithm that calculates that blurred contribution from the rest of the field. And so the difference here is the original one I showed you, all the atoms contribute, and it has quadratic complexity. By adding a cutoff, we're just doing adding the atoms within that circle, and we've improved the time complexity. And this algorithm then can then be adapted to service many different variations. Anything that has a spatially evaluated potential function with a cutoff can be adapted to this sort of computation. So showing you the sort of the overview of how this will work. we'll take some of the things we learned with the direct summation approach and we'll apply them with its cutoff. But there are going to be a few differences. So in this case, rather than storing the atoms in constant memory, which was very successful last time, we need to use a different strategy this time because we're going to use this cutoff scheme and we have multiple complex data structures to deal with. So the first thing is we will build a grid of atom bins. So rather than just hammering all the atoms through, now we have to consider, are these atoms within this cutoff sphere? And rather than calculating that for every atom redundantly, we're going to sort them into bins to begin with. So then we can do a test to see if a bin is a candidate for the cutoff sphere, and only if the bin is do we even load the atoms that are in that bin. So we will first stage those atoms into these bins. So there's a regular grid containing these bins. We will, during the calculation, we will basically pull in bins into shared memory. And the bins that we're going to pull in are based on a lookup table that we will have stored in constant memory beforehand. So we calculate the neighbor list for any lattice point and the offset index offsets to the neighboring bins that we will need to read in. So for any potential map region that we calculate, we refer to this table, figure out which bins we're going to need, pull those into shared memory, process those bins, add their contributions to that region, and so on. And so we just basically stream all this information through the GPU. But we're using some of the same techniques. We're amplifying the bandwidth of the device by using constant memory for this frequently accessed lookup table. We're using the shared memory to crunch through all the bins. And we can do it in a single pass. So we don't have to do a multi-pass algorithm anymore. This is all in one big loop. Yes?
That's basically neat, but how do you guys keep from mapping two atoms to the same bin when they're very, very close?
Oh, there are multiple atoms per bin, so that's another detail. Thank you for asking. So actually, each bin is not an infinitesimal region of space. It's actually a fairly large region of space. And our goal in decomposing this algorithm is to come up with a strategy that gives us an average of 8 atoms per bin. And the reason for that is so that we get coalesced memory access when we load those atom bins into the shared memory. So because we're solving a particular problem, in our case it's a biological system, we know the biologically average atom density in number of atoms per cubic angstrom. By knowing that, we can size those bins so that on average we should have 8 atoms per bin. There's one other trick we're employing here. So if we have fewer than 8 atoms per bin, it's rather like the padding that I referred to in the other calculation. If we only have 6, we're going to do the work for the 2 blank or empty slots, even though there's no atom there. If there are more than 8 atoms, now we have a problem. What do we do with the atom that won't fit in the bin? The strategy we're going to take there is to handle that as an exception and have the CPU do that. So we actually have, and the reason for doing this is then we have a high average occupancy of atoms in the bins, and the GPU performs the best when all of those things are full or very nearly full. So that's our goal. So we will actually fill them to the point of overflowing, and as long as there's only a small ratio of overflows to full bins, we can then do that exception handling or cleanup on the CPU, and the GPU runs at a much faster speed, and it gives the CPU something constructed to do while it's waiting. And so that's exactly what I was just going to get to. So by doing that, we're sort of using the CPU to optimize the performance of the GPU, and that can make a big difference on our speed up. So we're regularizing that workload by planning everything just so that the GPU is mostly full.
So does that imply that you're passing that atom point back into some CPU memory unit?
Well, the CPU had them all to begin with.
Okay.
And so as it's building the data structure that the GPU is going to use, when we're building these bins in the first place, when we hit the 8th slot and we have one more atom that maps to this bin, the CPU makes a note of that and says, uh-oh, I have 9 atoms. And it goes and builds a separate auxiliary data structure that is the cleanup work that remains. And right after it launches this calculation on the GPU, it returns to its cleanup work pile and goes through and does whatever remains.
The neighbor list is just an array of offsets.
That's correct. Yeah, he was just asking, the neighbor list in constant memory is just an array of offsets. That's correct. And it's done as they're relative offsets because that way it applies equally to all grids and bins everywhere. So it's not a complete special table for the whole space. It's just what's required to do the calculation for each of these regions for however many surrounding bins. Another question.
You guys have very precise bins, so we have these space decompositions, right, where they repeatedly divide space one smaller.
Like Noctree. He was asking, did we consider using variable sized bins? For our calculation, no, because we knew that we wouldn't need it, and it would add addressing complexity. So well, the atom's coordinates are random, but their density is very predictable. Because if your atom density were to change wildly, you would feel very bad right now. So for biological structures, which is what we're doing, that wouldn't be a problem. However, if we were doing astronomy, for example, if I was doing cosmology and I was simulating the formation of galaxies with a billion stars, they have that problem in a big way. So they have a very non-uniform particle density, and so they have to use data structures like octrees where they can adapt to the particle density dynamically. But we're lucky. Since we're working with biological structures, and which most of our bodies consist of water, we have a very uniform particle density. If it changes radically, the patient's dead. So we didn't have to worry about that. So I'll show you one interesting thing here. So the original piece of code we wrote for this, we started using the CUDA streaming API, which is something new that they added in CUDA 1.1. And this was an important feature for us because it allows us to schedule grids of thread blocks to the GPU, and then the CPU can immediately return and continue this cleanup handling I was referring to. This gives us the opportunity to have the CPU do the cleanup work for the non-uniform bins that the GPU didn't want to do, and it can then pull and determine when the GPU is completed. But there's a limit, at least somewhere there's a limitation there, in that you can only submit so many asynchronous kernels before the GPU is full. And once it's full, it will actually block the CPU until it's processed enough that the queue drains slightly. So we were actually unaware of this when we first wrote the code. So you see the performance goes up very rapidly. We get to a speed up around 21, 22, and then you see it begins to taper off. Well, it turned out the reason it was tapering off is because at this point we were submitting so much work in the asynchronous queue in CUDA that the GPU was then forcing us to wait. But for whatever reason, we didn't pick this up in the first version of our code. So we were puzzled by this. So once we figured out that that was what was happening, we changed our code so that rather than decomposing our grid into individual slices and queuing those up one at a time, we were doing much larger chunks or a slab or the entire volume in one go with one bit, adding another loop, which consumed a register, which is why the peak speed of this code isn't quite as fast as that one. So that cost us one more register than we'd used before. But the benefit of making that change is now the code doesn't fill that asynchronous execution queue with a massive number of jobs. It's just 1 or 2 or 3. It's a controllable number. And so we have predictable performance that won't change as the problem continues to get bigger and bigger. Any questions on any of those things so far? Okay. So now I'm going to switch gears and tell you about NAMD. So besides calculating these electrostatics, we actually want to simulate the motion of these molecular structures. And to do that, we have a program called NAMD. And NAMD calculates the forces between the different atoms in the simulation using electrostatics as one of the terms in the force calculation, but there are actually many, many others. So NAMD works by taking bins of atoms, which in NAMD parlance we call these patches. So space is decomposed into little cells called patches. The atoms in each patch, it uses a cutoff algorithm like the one I just showed you a minute ago. And we compute the interactions between atoms that are within a cutoff distance of each other. And so that involves calculating distances between atoms and neighboring patches and computing their interactions. Now, one thing you'll notice is that if there's n patches, there's actually a much larger number of interactions than patches. So a strategy that NAMD uses to give it much more concurrency is rather than breaking up the work purely spatially, which is what a lot of codes do, NAMD instead breaks up the workload or the interaction space. So it has both a spatial decomposition as well as an interaction decomposition, and this gives us a tremendous amount of concurrency to work with. And so this is a strategy that lets us run on thousands of CPUs on clusters. So of the calculations that NAMD does, the one that is the most time-consuming is what's called the non-bonded electrostatics interaction, and that's basically like the cutoff calculation I just showed you for the electrostatics code. So you can see the number of different interactions that NAMD is calculating for a typical simulation, and the non-bonded interaction is the magnitude of the work objects here is huge compared to the others. So in a CPU-based cluster, this would be 90% of the runtime for the entire program. So this is obviously what we want to accelerate by running it on the GPU. And so NAMD basically calculates all of these things asynchronously, and it sort of juggles this giant pile of work among all of the available processors. And so one of the things I should mention is by offloading this to the GPU, this immediately frees up the CPU to do all these other things. So the way this is mapped onto the GPU is very similar to what I just showed you with the electrostatics kernel. We bring in atom information and things like this into the constant memory and into the texture unit. So we have atom information such as how these atoms are they bonded, are there special force exceptional cases where we calculate a different type of force constant than another. We have an interpolation table to help us do IRC, which would be a very expensive calculation to do on the GPU, or in fact, even on the CPU, we use an interpolation table. And we basically stream these things through the GPU in much the same way we did with the electrostatics calculation. This is, just to give you an example of what a complicated CUDA kernel looks like, this is the non-bonded calculation inside of NAMD. You'll see some of the calculations are very similar. You see the distance calculation up at the beginning. There's a cutoff comparison. If the cutoff fails, then we're done. If it succeeds, then we start doing a force interpolation. We determine if there is a special case that has to be handled where we wouldn't want an interaction between those two atoms, and then we adjust various parameters and apply that force to the atom, and finally we accumulate those forces for each atom, and that's then the beginning of integrating the motions of the atoms. So that's actually how it's working. So you can imagine like that the particle pairs that were being calculated in the potential code that I showed before, we had interactions between those neighboring atom bins and their corresponding lattice points. In NAMD, we have actually interactions between the atoms themselves. So there's much more going on there. If we take all of those patches of atoms and we distribute them across multiple processors, each processor owns some of those atoms. In order to proceed with this calculation, they have to exchange their information with their neighbors. So this calculation decomposes into two pieces, a remote part and a local part. In order to get the best performance, we want to decrease the amount of time it takes for us to provide our neighbors with the information they need. So actually what we do is we prioritize the calculations that our neighbors need from us first, and we do the ones that we only need for ourselves last. And so this is a tricky thing to accomplish because we need to keep the GPU and the CPU busy. So the strategy for doing this is to basically load in the atom coordinates from our neighbors that we got from the last time step, put them on the GPU, and immediately begin computing the remote forces. So then we get the GPU busy. The CPU then immediately begins doing the same thing for the portions of the calculation it's responsible for. After that's done, the CPU continues polling here. So this is an asynchronous operation in a CUDA stream, and the CPU keeps checking to see, is it done yet, is it done yet, is it done yet, is it done yet? When it is done, we get those forces back, and we immediately send them to our neighbors. And then we continue having the GPU calculate just the local force calculations. And all along this process, the CPU is basically continuing with the rest of the work, all the other calculations besides non-bonded interactions. And then finally, at the very end, when we get the local forces back from the GPU, we do the time step integration, and the atoms are moved to their new position, and then we communicate with our neighbors, and the process begins again. So to give you an idea of how that works on a cluster of GPUs, we implemented this on the NCSA GPU cluster that you've seen upstairs. We were able to use up to 60 GPUs. We would use more, but there were a couple that weren't working at the time we ran the experiments. So there's an interesting trend here. You'll see with a small number of GPUs, the amount of local work relative to the amount of work that our neighbors depend on is very large. As we start using a larger and larger number of processing units, GPUs or otherwise, that ratio changes, and the remote work starts to get to be a larger and larger percentage. And if you go really far, it eventually becomes the dominant calculation. So that explains why it's very important for us to prioritize that the highest. You can see also the magnitude of the time spent on just the GPU portion of the calculation. We started at half a second, and by the time we're up to 60 GPUs, we're at 400ths of a second. It's a very small amount of time. So the overheads for things like network transmission, latency to send things back and forth between the host and the GPU, the host and the InfiniBand card, all those things start to become a much bigger issue. And the entire time for the calculation is only 85 thousandths of a second. So it's very fast. And this is approaching sort of the upper limit of what the network can handle. What's interesting to observe here is at 60 GPUs, even with only a speed up of 5.5 here, this is like having 330 CPU cores, but with only 16 InfiniBand cards. So that's it's the equivalent of having like 20-some CPU cores with one InfiniBand card. It's very sort of out of balance. And so this is going to be an interesting challenge as things go further, because if we want to build a really big GPU cluster, we're going to have to find a way to improve the network performance. So you can see on this graph, here's a sort of a pictorial representation. With one core, it takes 25 seconds for the CPU to run one time step for this problem. If we run this on the GPU, we bring the entire runtime down to 3.5 seconds. Just the GPU portion is just over 2 seconds. And this is all with G80. These numbers are much better on GT200, as I'll show you in a minute. As we get faster and faster and faster, the work done by the GPU becomes vanishingly small. And so that begins to indicate an opportunity for us to start to move other calculations besides the non-bonded interactions to the GPU. So I just had one of our colleagues at NVIDIA help us out by running the same code on the new GT200 cards. So these aren't the actual production cards. These are slightly slower than the final product, is my understanding. But with 8 GPUs, we're now getting a speed up of 9 with the pre-production hardware. Then that means that with this little tiny 4U box, we're getting the same speed that we would have gotten with 72 CPU cores. So it's very impressive because this is just 4 U's of space and much lower power consumption, and we're getting tremendous speed ups there. So that's 32% faster than we were getting with G80. The CUDA portion is actually 54% faster. We lost some of the benefit from the GPU just to the network bottleneck. So in a similar way, I believe there are only 4 InfiniBand cards in this case. So it's still, even though it's a lesser overload situation than we have with this cluster, there's still the ratio of computation to network is tremendous. Another thing I noted in this run is we have an 8% variation of GPU load. So some GPUs have about 8% more work than the others. So one thing that we need to do to further improve our performance is to get that load balanced. And so this is tricky because at the moment the GPU is invisible to the runtime system that does the load balancing. It actually has no idea that there's even a GPU there. So this is one of the, in the future we're going to have to adjust that so that the load balancer knows about the GPU and knows how to shift work back and forth between the GPUs on other nodes. Another interesting thing, so the GT200 is the first card that has double precision. And I did some experiments with this. And the most important part of that big non-bonded kernel as far as precision goes, is in the accumulation of those forces. And the reason for this is because you'll be accumulating minuscule tiny forces along with forces of very large magnitudes, and that's, of course, a worst-case scenario for floating point accuracy. And so in order to improve that, we have basically the choice of using things like compensated summation, changing the ordering, or using double precision. The nice thing is on GT200, we can just change the type from float to double, and that only cost us 8% performance, even though double precision arithmetic is significantly slower than the single precision arithmetic, because it's such a small piece of the overall calculation, and there's only a certain statistical chance that we're even going to get that far, and even in a given iteration of that force loop, the cost is basically negligible. It's completely hidden by the other overheads involved, like the network and so on. So just to give you a summary of some of the other kernels that we've been developing over the last year, these are some of the speedups that we've achieved on different codes. So one is fluorescence microphotolysis code that basically takes a 2D matrix representing a microscope image and running a reaction diffusion equation on it in an iterative manner. This one had very difficult boundary conditions, and so that presented a challenge, but we were able to get a 12x speedup, which is essentially memory bandwidth limited. And it only took us, where we may have spent a grand total of 120 hours tuning the CPU code, I think to get that 12x speedup in CUDA only took us about 20 hours. And so it was a lot easier in a way than what we did on the CPU. Then you can see some of the speedups we get for particle pair distance tests. So this is another way of calculating these particle interactions. If you can pre-compute a list of who your neighbors are, if you already know who your neighbors are, you don't need to do that repetitive cutoff test. So that avoids that cutoff test. For very coarse grained particle systems where you have a low density of particles, it actually is beneficial to use one of these pair lists instead of doing the raw math. And so this is something we're looking at for doing coarse grained simulations. And I showed you the cutoff force calculations. And electron density summation is very similar to the potential summation I just showed you, except for it has the nice property of mapping exactly to one of the exponential instructions that the GPU has. So this is something that we expect with a little more tweaking, we should get speedups in the range of 40 or 50 versus the CPU. And then multi-level summation, the first part of that algorithm is that cutoff summation I just showed you. And there's another half to that that is a grid convolution that takes care of long-distance, long-range potentials that are contributed from much farther than the cutoff distance. And so we get very similar speedups on both halves of that calculation. I don't have the number right in front of me, but I think the speedup we're getting now with GT200 is about 35 for the two combined, which is tremendous. And that's a linear time algorithm. So this is something that we hope to use to replace one of the bottlenecking algorithms in AMD eventually. And then, of course, I've shown you the direct summation. So sort of the take-home from the work that we've done is that when you're designing your GPU algorithm, you want to decompose it in such a way that you have a tremendous amount of fine-grained parallelism. David and his staff are continually doubling the number of processing units, and so are all of their competitors. And so it's important for you to start thinking not in terms of tens of processors, or maybe even 100, but think about 1,000 processing units. How could you decompose your problem to give you enough concurrency to keep thousands of processors busy? That's the way you should be thinking, because before you even blink your eyes, it'll be 2 years from now, and there'll be machines that'll be mind-boggling. But to keep them busy, we have to decompose that work into very small pieces. Working at the next level up, using multiple GPUs, if you think of a multi-level decomposition, you can then, for example, in the potential map calculations, we cut these things into slabs or into slices, and then cyclically decompose that onto multiple GPUs. There are many opportunities for doing such things in many different problems, so keep that in mind. And it's very easy. It doesn't take much effort. If you can do it in a sequential code, doing it in the parallel code is just as simple as distributing the work and doing the halo exchange between neighbors. And a key thing to keep in mind going forward is that the trick to GPUs, you have to get over, if you've been tuning code for a long time, the hardest lesson I had to learn is I've spent 15 years trying not to do floating point operations. On the GPU, that's the wrong strategy. Don't try to be clever. Do the floating point operations. Try to avoid the memory references. Try to avoid reloading that data. That's going to be the thing that matters going forward. Don't try to be frugal with the flops. Use the flops. They're your friend now. They're no longer the enemy. Look for opportunities to use the CPU to regularize the work that the GPU is going to do. If you can make the GPU 95% efficient instead of 80% efficient by doing a little bit of pre-processing and maybe handling, like I described in the other code, if your CPU can handle 1% of the work and make the GPU 15% more efficient, that's a very good trade-off. So look for opportunities to use strategies like that, fixed size bins, things like that. They have a very good chance of paying off. When you're looking for pieces of work to parallelize with the GPU, you want to look for something that's a significant fraction of your runtime. If it's not, this is the limiting factor. When you see different speedups for different codes, just because somebody only got a 3x application speedup from their GPU doesn't mean they didn't know what they were doing. It often means that the portion of the code that was easy for them to adapt to a data parallel execution pattern just happened to be only 30% of the runtime. So that's another thing to keep in mind. You'll see a huge variation in the speedups that people get, and some of that is just AMDAL won't let you go any faster than that. And of course, using the new streaming API, this is a big deal. Having the opportunity to use the CPU and the GPU together is something new that's been made much more effective in CUDA 1.1, and I'm sure even better in CUDA 2.0. If you can find a way to keep the CPU occupied or processing the things that the GPU isn't going to do for you, whether that's handling message passing between nodes, doing calculations that aren't particularly data parallel, things like that, if you can do those at the same time and have the CPU pull for the GPU's completion or use other strategies, that's another opportunity. And then these are some of the publications that describe the algorithms I just talked about. Are there any questions? And I got done earlier this time. one time I gave this talk for 1 minute, I think it was an hour and a half by the time I got out of there after all the questions.
We're doing better every time.
Yeah. Yes? Yes, well, as I showed in the, she asked if I tried any smaller molecular systems besides the virus simulations, and the answer is yes. You can see we ran tests all the way down to 100 atoms, which is, sort of a toy. That's practically a pharmaceutical at that point. So, at this range, I looked at the size of the structures that are in the protein databank, and everything of interest is, at least 10,000 atoms. Only the oldest structures are that small. All the stuff that's hot today is in the 50 to 90,000 atom range, which is dead in the center of the sweet spot for the GPU algorithm you see right here. And of course, that's not an accident. I went and looked at what's the statistical distribution of problem size of interest, and I tuned my kernel so that it was right in the center of the area I expected us to want to do. Next question. Mm-hmm. She asked, comparing the results from single precision to double precision, is it significantly less accurate? In our case, no, it's not significantly less accurate, but we weren't looking for pure accuracy for the application we intended. What we were doing is using those maps to find minima in the electrostatic field, so as long as we don't get a false minima, it's okay. And it was more than adequate for the intended application. That's why we were eventually able to use the cutoff method, and it's more approximate in the first place. But it is important to do the summation to prevent floating point truncation, and so we did use compensated summation and other tricks like this to further improve the accuracy of the algorithm. Actually, I believe for this code, doing compensated summation, I don't know how many of you are familiar with that, but you can actually use two accumulators, and instead of when you add a tiny value to a large value, instead of the tiny value being thrown away or lost, truncated, there's a way that you can do this calculation so that the part that would have been lost goes into a second accumulator. And so by doing this, you preserve the contributions of the small values. And that's an important thing because I could have an electrostatic potential from two nearby atoms or a nearby grid point and a nearby atom of very large magnitude, let's say 10. That's let's say a very large magnitude. Then I have 10 billion atoms that are of minuscule potential contribution. If I want to get the right answer, it's important that I not truncate those little minuscule contributions because if I have a billion of them, they will add up to an overall larger number than the one that was in there. So using compensated summation or double precision can be important for that, and that's what the gentleman was asking about. Fast multipole is another algorithm one can choose that preserves that property. You had a second question. So that's an interesting question. She asked, what's the upper limit on the number of atoms and time scale? So fundamentally, there's a huge gap between the speed of the fastest computer in the world and the speed of the things that are happening in your body. The longest simulations anybody has ever run, really, at this level of detail, are on the scale of below a millisecond. And so the goal is to be able to simulate things that are milliseconds in length. At the moment, even doing something that's a fraction of a millisecond can take a year running on hundreds of processors. So using GPUs, we're amplifying this tremendously, but it doesn't change the fact that we're still missing by several orders of magnitude. So what we do is we study the things that have a time scale within the reach of today's computers. But this is why people keep wanting to build larger and larger supercomputers. Yes?
So what time scale do you think we can reach with your current setup? Yes.
So for the potential field calculation, there's no time. This is instantaneous snapshots. The limitation here would be what's the number of atoms. For the iterative calculation, for the linear time calculation, let's see if I have a plot here. You can see that, well, I guess I don't have the absolute runtime. Well, it's a matter of seconds with on the order of 8 million atoms. The systems that we're interested in doing these calculations for are limited by the size that we could ever hope to simulate typically. So we're probably, in the next 4 or 5 years, we're looking at systems maybe 100, 200 million atoms in 5 years. And that would be the upper limit, and even that is very, very difficult. So that would limit the size that we're interested in ever solving, at least right now.
So 100 million atoms for 1 second?
Yeah, that would be very challenging.
Okay, so what you're, because I use scale, and I'm trying to figure out what time scale you guys think you can get up to.
It depends. If we're talking coarse grain, the time scale is much longer. For an all-atom simulation, I don't actually know the answer yet. I think much will depend on what huge supercomputer we have to run on and whether or not it contains GPUs. If it contains GPUs and we're getting factors of 10 or factors of 20 faster than we do now, that's obviously a big amplification. So it's hard to say, though. And it depends on how things happen methodologically. We could adapt to new algorithms that give us better results, but they might cost us more time for time steps. So if we use polarizable force fields, things like that could cost us something. If we don't, or if we use a simpler method like coarse grain structures, that might give us a much longer time scale. But that's not really my area. So, yeah. Next question. Right. This gentleman asked, what's the limit of scalability for the CPUs and the GPUs together? I would say at this moment we don't know. I would say at the moment the limit isn't so much the computational side of things, it's the communication. So you can see with 60 GPUs, whoops, wrong direction. With 60 GPUs, we are starting to see the speed up tail off with 4 GPUs per InfiniBand card. Clearly, to build a much bigger cluster, we'd want to change the ratio so that there's maybe a 1-to-1 GPU to InfiniBand card mapping. Instead of using single data rate InfiniBand, we'd want to use quad data rate InfiniBand, but these things cost money. And so the answer to that question depends on the size of the structure. The larger the molecule we simulate, the slower the time step rate, the slower the communication, and the more computationally demanding it is. So it could be, depending on what the machine is. For this machine, we would prefer large molecular structures, which give us a good local to remote ratio, right? That's going to be required for this machine because it just doesn't have the communication faculties to do it. If we built a different machine that was targeted towards simulating small structures much faster, we might have a very different ratio of hardware. So it just depends. I don't think there's any limit except for what hardware you're able to buy and the speed, how efficient the software interface to InfiniBand and the GPU is. And these things are continuing to evolve. So if we could cut down on various sources of latency, they're just software issues. For example, doing DMAs from the GPU straight into the InfiniBand card, or in a future GPU, maybe they'll make a GPU that can do the communication between the GPUs for itself, and you don't even need the InfiniBand card. That would be great too. I don't know the answer at this moment. Next question. Yes. 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 Her question was, the fixed size bin model that we're using for our this algorithm is because we have a fixed, or basically a relatively fixed atom density, and that's a result of using explicit water in our simulations. And the answer is yes, this is for explicit water simulations. But actually, even in the case where there's no water, so we do some of these calculations on structures in vacuum. So for ion placement, we do it with no atoms where the water is. In those cases, you will end up with bins with 0 atoms. And so we have a special case to handle empty bins too. But if you were really slick, what you would do is if that was important to us and we had a huge volume, let's say, we would actually adapt an outer loop that would only pick up bins and coarse tiles where we knew there was structure. So this is a big consideration, for example, as we go to doing electrostatics calculation on a 100 million atom model, for example, like they're preparing for blue waters, chromatophores and things of that sort. There will be a huge volume, and when we're preparing a structure and placing ions and things like this, the majority of the volume will be empty, so we'll have to write special case code to skip entire groups of bins. And that does quite well. So then it'll just be the areas of the structure at the boundary, so the surface water, where there would be surface water, you'll have bins that are less efficient, but most of the volume is occupied with structure of interest, so it's not a big performance hit. So it's just the surfaces where you pay that penalty. But you could adjust the bin size. We could have used a bin size of 4 instead of a bin size of 8, so you can choose what that is. They're just trade-offs in the efficiency of different parts of the code, and you can juggle those things around a little bit. Another question?
So John, you touched on two things that which extends the contents from the previous lectures. One is the multi-GPU, and we didn't talk about multi-GPU. And the other one is using CPU to
regularize
and also to fix up some of these problems. And conceptually these are not that hard to understand, but when it comes down to mechanics, it does require quite a bit of infrastructure support and code crafting and so on to make these things happen.
And you have to understand what assumptions you're making when you decompose the problem in the first place. She was asking, well, are you going to do explicit solvent or implicit solvent, and will that have an impact on your problem? Well, we did think about what if we use this when there's no water as an ion placement calculation. That's one case. Another case is when there is water and they want to look at the electrostatic field for the fully simulated system. Those are two different use cases, and we pondered what percent of these bins will be completely empty. And then we added a little special case that actually handles the empty bins more efficiently than the original version of the code. And then we thought, well, let's see if anybody complains. Does anybody notice a performance artifact there, or is it fast enough? That's the way we begin. So all of these things, we could make more kernels for each of the different cases we care about. But you're right that it does not. The trick here is we had to start from an understanding of what we were doing. What is it we're simulating? What are the trade-offs we're making in the physics that affect what we do? What choices we make here? And where is it going to be in 2 years? Are we going to do the same physical model, or are we going to change something like adding polarizability? Does that have? Do we have to deal with that in here, or is that something we can ignore? Those are all interesting questions.
But I totally agree with that. But when it comes down to the programming mechanics, my guys have been using your multi-GPU setup, and but there's also I see some of these setups where you can overlap the GPU and CPU execution, and the CPU can use there's some mechanics in general that you need to have in order for that to happen efficiently and safely and so on. And are you also thinking about making some of these things into more like almost like a framework structure that to help people to do something along those lines?
Yeah, I've been thinking about it for a while. It's tricky to come up with something that's both easy to use and has a high probability of being useful for a large diversity of problems. So that's one of the things I was trying to figure out is, well, how do I take the code that I've written for some of these things and give it to somebody else so that the part that they're concerned with is mainly getting their CUDA kernel right and providing the scheme to do the IOs between the different GPUs and then let the framework handle those things. And doing that well is kind of tricky because the devil's in the details. How does that relate to the big picture? Do you need to have the CPU and the GPU continually communicating with each other? Some of the things we're doing with NAMD have been very educational for me in terms of the special problems that come up. The way we do it now is not necessarily the way we'd ideally like it to be. If we had our choice, what we'd like to do is submit all the work to the GPU at once, but have a priority assigned to the ones that we want done first. And then we wouldn't have to pull it as frequently. We could say, oh, well, this remote work and local work together will likely consume 100th of a second, so we don't even need to check until at least 100th of a second has gone by, and it makes the whole thing easier. So these are things that I would expect to change too. This is the way we do it today with the current generation GPUs and APIs. As they evolve, it might remove these problems altogether. There would be no need to do it this way. This is the way we do it just because that's what's available. So that once those things simplify, then it'll probably be a lot easier to give a framework that works in a broader diversity of cases. Yeah.
Maybe last question.
So his question was about load balance, whether there's a need to do that on the GPU, whether there's a need to do it across a cluster, how much imbalance there is. Within a GPU, the hardware thread scheduler is doing that for us. If we could get it, like I was saying before, if we could actually have multiple CUDA streams feeding into that hardware thread scheduler and have priorities on them, it could do even more for us than it is now. So that would be one thing we'd like to see. But really, other than that, at least with the kernels that we've developed so far, there was no need to worry about what the hardware is doing within one GPU. So far, other than that one feature request, it's fine the way it is. But definitely, as soon as you have multiple GPUs, you will have load imbalance. That's the nature of parallel processing. Even within one GPU, if you don't have a number of thread blocks that tiles evenly into the number of SMs, you'll have some SMs that are imbalanced, but the only thing you can do about that is either to add more work as it's completing stuff that's already running, or find a way to decompose it so it exactly divides into the number of SMs. So that's the limitation on what you can do within a GPU. But across GPUs, there will be some load imbalance. A good example of that, so you saw this huge kernel that I showed earlier. There's a statistical likelihood of this test passing or failing. Some threads will complete this part of the code early, and some will complete it late. Now, because of branch divergence and things like this, an entire warp will either have to walk through this whole piece of code, or if they're lucky and they all finish early, then it'll run a lot faster. So some of the load imbalance just happens to do with statistical likelihood of different parts of the kernel executing at different times, whether or not there was branch divergence or not. So that even if you had an even number of interactions across all the GPUs, the statistics of this if test going one way or the other, and whether or not it's a whole warp or just a fraction of a warp, can imbalance something that you had thought at the beginning would be balanced. And so yes, you do have to do some sort of load balance. With stuff like this, if we were really sneaky, what we would do is we would sort the atom pairs by their radii into warps that have a coherent, at least a high statistical probability of a coherent branching. So this is something with a long code path like this. If we could get all the threads in one warp to always go the same way, that would increase the efficiency of this thing overall. So this is something we'd like to do. So that would be one way to improve the load balance, make sure that the warps are always behaving in a predictable manner from one cycle to the next. And then the other thing is just being able to shift the work back and forth between the GPUs. You were asking about Charm++. So NAMD uses Charm++ as the scheduling layer to distribute work to all the different CPU GPU pairs and to do the dynamic load balancing, reevaluating the runtime. So this is one of those little things that we have to tweak in our GPU implementation. At the moment, Charm doesn't even know that there's a GPU there. What we're doing is we're taking work that Charm gives us and we're handing it to the GPU and saying, oh yeah, we're taking care of that for you. And it gets back way faster than Charm++ was prepared for it to happen. And it has no idea how we're doing that. And so Charm++ is basically blind to this. And the trick is, so we have to give it this information. And the thing that I was going to tell you is that AMD was designed to balance this part of the work. This was 90% of the runtime before the GPU came along. So that it used to be, we didn't even have to bother with shifting the other pieces of work to adjust load. Now that the GPU is here, this is of the same, at least runtime-wise, it's more similar in magnitude to all the other work added together. So now, besides the fact that there can be GPU imbalance, now the imbalance created by the other computations is no longer insignificant. Now it matters. So now we have to think about load balancing all of these things, not just this one piece. So we have a number of opportunities to improve the scaling of the GPU version, and it's a little bit tricky because now we have to enter territory that nobody's touched in 10 years. So with an old code, even something as young as NAMD, there will be pieces of code that you have never tuned because you thought 10 years ago, well, this will never be a performance bottleneck, but it turns out that it is. As soon as you put an accelerator that gives you a 10x speed up, it turns the world upside down. Now all of a sudden pieces of code, I'll give you an example. There was a piece of code that nobody had tuned since the late 90s, and we started running some tests on the GPU, and it was using 30% of the runtime for a little tiny piece of code this long that was badly written. And by rewriting that code, I got it down to 5%, but it hadn't been touched in years. And the assumption was this will never be on the critical performance path because how could it be? But it is. Once you throw a GPU at the big part of the problem, it just squashes that down to a small piece, and now Amdahl has a different impression of what's left.
So let's thank John again.